This is the fourth section of the Methods in Calculus chapter, and here we're going to be looking at integrating inverse trig functions. Now the last section was differentiating inverse trig functions, and these results here are in the formula book. So when we go from this side to this side, this is when we differentiate. So it does mean that we can use these results backwards to integrate. Now when we go backwards to integrate, what we want to try and get to is, well, what we're interested in is, see this x that appears here, we've got like an x here. Now if I've got something other than x there, let's say, I don't know, let's say this was 4x, then I need to appreciate that I'm going to get a 4x over here. If this was, I don't know, x over a, then over here it's going to be an x over a. So as long as we use an appropriate substitution, so what we're looking for is this bit here, and maybe we would make u equal to 4x, u equal to this bit here, u equal to this bit here. That's what we're interested in. So the method, the technique for these is to use substitution, making u equal to the x part. Now what I mean by the x part is this bit here. It would make u equal to that, and then that means when we go over to this side we're going to have arc sine u, arc cos u, arc tan u, and then we can substitute back. So that's the method we're going to use. So we really want to make our questions look like this. They need to be one of these three formats. Okay, so by using appropriate substitution, show that this integrated becomes arc sine x over a plus c, where a is a constant. Now you'll notice in all of the results that we had for differentiation, this was the number 1. So we want to make that the number 1. It was either 1 minus x squared for arc sine and arc cos, or 1 plus x squared for arc tan. So let's write out the question here. So square root a squared minus x squared. So step number 1 is going to be to factorize out the a squared. So a squared 1 minus x squared over a squared. Then the square roots can be separated out like this. Now the 1 over a squared, the square root of a squared is like 1 over a, which is a constant, so we'll take the constant over to the other side of the integral sign, leaving us with this. So 1 over the square root of 1 minus x squared over a squared. Now here comes the substitution. Now remember, they all had x squared, the standard results at the end. So really what I want to do, I suppose, just to make the substitution really clear, is to write this as the square root of 1 minus x over a all squared. So there can be no doubt about the substitution there. We'll let u equal x over a. Now that means we'll want du dx, which will just leave us with 1 over a, the coefficient of x. And now substituting, so I have 1 over a, and then 1 over the square root of 1 minus u squared. This is my substitution. And I suppose over here dx then equals a du. Yeah, if you multiply both sides by a and multiply both sides by dx. So I actually have a du. Now you can see that these cancel out, the a's there, just leaving me with integrating 1 over 1 minus u squared du. Now just write down that previous result from differentiation, which was when we differentiate with respect to x, arc sine x, we get 1 over 1 minus x squared. So if I use that result here and use it backwards, I will get this integrated as arc sine u. Yes, I'm just using this result backwards because if we match it up, where I've got x, I'll just replace it with u. So I now end up with arc sine, in the right colour, arc sine u plus c. Then we substitute back because up here we said u is x over a. So finally we can write down arc sine u, which is x over a plus c. So we've proved it as required. So before we have a look at this example, let's just talk about what we've done, which is actually worked out or derived from scratch the result using substitution. But there are these two results which are in the formula book, so you don't need to memorize them, and you can just use them without further proof. So this isn't the question that says show that this equals something, where we would use substitution like in a previous example. Here where we can just use one of these two results. So the first thing we're going to do is take the constant over. That should normally be your first step, like this. And then because we're using one of these two results, we just want to see which one it matches up with. Well, it matches up with this one, doesn't it? Yeah. If we make a, this needs to be something squared, so a needs to be square root 5, so a equals square root 5, and then without further proof we can just write down our result is going to be 4 times by 1 over a, which is square root 5, times by arctan x over a, so that's x over square root 5 plus c. So we could leave it like that, or we could just say 4 over square root 5 arctan x over root 5 plus c. Okay, so we've got two integrations here. There's nothing about show that your result equals something, so we don't need to prove anything. We can use these standard results here. So all we do is compare what we have written here with the standard results. Now I can see I've got something plus something squared, so it's going to be the arctan one that I need to use. So the first step is to get it to look like this. I cannot have a number in front of x squared, or its coefficient needs to be 1. So let's just write the question out, and the first thing I'm going to do is to factorize out that 9. So I get 9 and then 25 over 9 plus x squared. So that's the format I want it in. Well, not quite, because I'm going to move the 1/9 over like this, and then I've got 1 over 25 over 9 plus x squared. So can you see it's now in the format that's here? So x squared, or a squared, from that result is 25 over 9, which means that a is 5/3. Now I can just use that straight in the result. So I've got 1/9, which is my factor of, and here it's 1/a, so it's 1/5/3, arctan x/a, okay, plus c. So all we do now, tidy that up. So 1/9 times by, let's work that out, 1/5/3, in other words, a 1/9, 1/9 times by 3/5 basically, because that's going to get flipped. So that's going to be 1/15. So 1/15 arctan x/5/3, which is going to be 3/5 x plus c. So that's it. Very straightforward once we know we can use those standard results. Okay, part B. Here we've got some limits, and our limits are √3/4 and -√3/4. And we need to integrate this. Square root 3 minus 4x squared. Now we compare it with our standard results. Notice that I've got a minus here, so it's going to be this one. Again, the coefficient of x can only be 1 for us to use this result, which means taking out the 4. So √3/4 minus √3/4, and we take the 4 out. Yep, so 4, and then in brackets 3/4 minus x squared. Right, now this bit here, it'll become 1/4 times the square root of this, so I'll end up with a half, which I can take over like that, leaving 1/the square root of 3/4 minus x squared dx. Mustn't forget my limits, which will happen to that square root sign. So square root 3/4 negative √3/4. Right, now I can use my standard result up here. So a squared is going to be 3/4. So let's just do that in a different colour. So a squared equals 3/4. So a is going to be the square root of 3/4, which is √3/2. So now we can go straight to our result, and wherever I see a, I put √3/2. So it's just arc sine x over √3/2, which is the same as x times by 2/√3. So 2/√3x, and my limits, √3/4 negative √3/4. Right, now so let's substitute. So I'll have half arc sine, so it'll be 2/√3, replace x with √3/4 minus arc sine 2√3, so this time we replace it with negative √3/4. Right, now using a calculator, we'll get half times by, so this bit here, arc sine of all of that, which is basically arc sine of half, works out to be pi/6 minus and then the arc sine of all of this, which is basically works out to be arc sine of negative a half, is negative pi over 6. So basically you got half times pi over 6 plus pi over 6, which is going to be 2 pi over 6 or pi over 3. So we end up with a final answer of pi over 6 as that integral evaluated with those limits. Okay, now for this one, you'll notice that this has got an x plus 4 at the top, and both of these have 1 at the top. Now we can split this integral up, so we can use the standard result on half of it, and the other half we'll just use the normal integration. So the first thing we're going to do is we'll split it up as x over the square root of 1 minus 4x squared plus 4 over the square root of 1 minus 4x squared. So it's going to be this bit here that we use the result for. Use result. Once we've tidied it up, because we can move the 4 across, and I'm guessing it's going to be this result here because of the minus at the bottom. So let's deal with each bit separately. So let's deal with this part here. So that can be written as x times by 1 minus 4x squared to the power negative a half. Now remember that standard result, which was if our integral looks like this, we can make it look like that, then actually that integrated is going to become 1 higher power over divided by that higher power. Now to make it look like that, this differentiated doesn't give you x, actually gives you negative 8x. So we're going to write that and then do our adjustment, put some sort of constant over this side to make sure it still balances. So if we write negative 8x 1 minus 4x squared to the negative a half, okay, so this differentiated here does give you negative 8x, but to make it balance I'll need to put negative 1/8 there. That means I can go straight to the result that I've got here, which just saves us a bit of time mucking around trying to differentiate something and guessing if it's right or not. So it's going to be negative 1/8, which was there already, and then I just do this to 1 higher power divided by that higher power. So that will be 1 minus 4x squared to the power half divided by a half. So from there I'll get negative a quarter 1 minus 4x squared to the half. Okay, so this is only half the answer. I'll put maybe plus c at the end. Actually, I'll put plus c here, but I'll remember there'll just be 1 plus c for the whole thing. So that could be written instead as negative a quarter square root 1 minus 4x squared plus c. So we got half our answer. The other half of the answer we're going to get, obviously we'll plus the 2, we'll take the 4 over. So we've got 1 over square root 1 minus 4x squared dx. So this is going to be a different method. It's going to be using the result. I can't have a coefficient of 4 there. It needs to be, and it's going to be this result, it's got to be a coefficient of 1. So that will give me 4 here, then 1 over, I'll take the 4 out as a factor. Well, it's not really a factor, but I'm going to take it out anyway. And then a quarter minus x squared dx. Now I don't have to run through all the steps, but you can see that this bit will just become 1 over square root 4 and then square root this. So that's basically going to become a half. So I'm going to have a half over here as a factor. So basically a half of 4, I'll just end up with 2. So these sort of things you should be able to do without having to write down all of the steps. So I now have 1 over square root a quarter minus x squared dx. So we just need to use an appropriate value for a up here. So a squared equals a quarter. Let's write that down. A squared equals a quarter, which means a is going to equal the square root of a quarter, which is a half. So that means I can just plop that into here. Now I need to remember there's a 2 in front, so I'll end up with 2 arc sine a over a half plus c, which we know is going to give us 2 arc sine 2a plus c. Sorry, not sure why I put a when that should be x. So let's just correct that there. So now we have our final answer. We just put those two bits together. We take what we've got written here for this half, what we've got written here for this half. Obviously we just need to write 1c at the end. And yeah, let me put the positive term first. So I will have 2a arc sine, not 2a, the a is part of arc sine 2x minus a quarter square root 1 minus 4x squared plus c. So there's our final answer. So the technique for this one was actually to split the original integral up into 2 parts. One part where we used actually a standard pattern, or you could use substitution to integrate to get this result. The other half, well, we could get it to look like one of these standard results, but written like that, you can't use any sort of standard result or any method. Yeah. So yeah, sometimes it needs splitting up into 2 parts, and then each part you can use a different method to integrate. You should now be able to do exercise 3D on pages 67 to 69. So remember, you can use these standard results that are here. You may be asked to prove them, in which case if you're asked to prove, you do that by using a suitable substitution. And the suitable substitution you're going to make is to use u for the x part. I've spoken about this right at the start, and the x part is going to be whatever you have here. Yeah, so if we had, for example, let's say this part at the bottom, we had square root of a squared minus x over 3 all squared, then you would say let u equal x over 3. That's if you need to prove it. If you're just finding an integral, then just use those results. It may involve, you may need to split up fractions, which we did on the last example. So if I had, I don't know, let's say something like 2x minus 3 over square root 25 minus x squared dx. Then you'd split this up so that you've got 2x over this part, and we've got methods for integrating that, so maybe substitution, or it may be that you use the standard pattern if you can get it to look like this. So we can use that pattern to integrate, whereas the other part, where you'd have something like negative 3 over the square root of 25 minus x squared, then take the negative 3 across, and it's probably going to be something like this here that we'd use to integrate the other part of it.